Okay, let's check the chapter 11. Chapter 11. The title is chi-square and ANOVA test. ANOVA test. About this part, to be honest, to run a calculation is easy, but if you want to know more details, it's not easy. Why? I can tell you why. Because in the past, our education, including when I was a graduate student in the US, when I learned biostatistics, it was very, very hard because the concept is, how can I say that? The concept of statistics is really hard, and it's impossible to us to lead and calculate, and later we can get a formula. It's impossible, and thus we try to memorize, or we can check the textbook for the formulas. But actually, in my opinion, it was really hard. But calculation is super easy. Just copy, paste, and you will get the data. But I always encourage you to learn more the principles. Why do it look like this? Why you look like this? Why we cannot do that? Because in the future, if you have chance, if you know the details, then you can find, okay, the computer, something wrong with the computer. You saw me, I miscalculated something because for example, one day I should have clicked paired t-test. I did it once when I refreshed the website, then I forgot to click for a second time. Then the result was not significant. Then one student reminded me I needed to click the paired t-test. I did it in the first time, but I forgot it in the second time. And the result is completely different. Okay, and now let's move to chi-square and ANOVA test. And the chi-square, okay, this chapter presents materials on 3 or more hypothesis tests. In the past, we have one, for example, in a t-test, we have one sample, one population, or two populations. But two populations is impossible to get all information. Thus, we select samples from population 1 and select some samples from population 2 and compare whether they are the same. Just a quick review. And there are dependent data or independent data. What's the difference? For example, in my bottle, I have oolong tea here. And oolong tea is very popular in Asia countries, and we know that drinking oolong tea, according to some research, it indicates that drinking oolong tea can lower cholesterol or blood pressure or sugar in blood. But do you have any evidence? Do you have any evidence? We need to check the scientific references. That's one way. And just as I mentioned, for the t-test, drinking the oolong tea, after drinking oolong tea, we can compare the difference. Then we run paired t-test. And if we have two groups of people, and we select some of them, they are called samples. We compare their living styles, their diet patterns different way. Then we can run the independent t-test. Okay. And now we are moving to chi-square test for independency. What does it mean, independency? In my language, I will call, are they the same? But academically, we don't use this kind of language. We use, are they independent? Okay, let's check here. Okay, remember, qualitative data is where you collect data and on individuals that are categories or names. Then you will count how many of individuals and particular qualities. Qualities. And an example that there is a theory that there is a relationship between breastfeeding and autism. Breastfeeding and autism. Yeah. And to determine whether if there is a relationship between breastfeeding the babies and autism, okay, researchers could collect the time period that a mother breastfed her child, and if that child was diagnosed as autism, then you will have a table containing this information. Now you want to know if each cell is dependent of each other. Remember, dependency says that one event does not affect another event. And now we can run this. And about this test, we can call it chi-square test for dependency. Okay, here, hypothesis test for the chi-square test. State the non and alternative hypothesis of the level of significance. Yeah, we are familiar with this. Non-hypothesis, the two variables are independent. Alternative hypothesis, the two variables are dependent. They have relationship with each other. Okay. Although state your alpha generally 0.05, it means 5%. Okay. State and check the assumption for the hypothesis test. A random sample is taken. Expected frequencies for each cell are greater than or equal to 5. Okay, the expected frequency E will be calculated later, and this assumption means E greater or equal to 5. Find the statistic and p-value. Finding the test statistic involves several steps. First, the data is collected and counted, and then it is organized into a table. Okay, let's move. Like this one. Okay, the expected frequency, cell A and cell B equals E, A and B, N times row total divided by N times column total divided by N equals row total minus column total divided by N, like this one. If the variable are dependent in the expected frequency and the observed frequencies should be the same. And later, we will use the example using rolling dice, and that's easier to be understood. Okay. Then you want to find total difference of all of these three differences. The larger the total, the smaller the chance that you could find that test statistic given that assumption of independence is true. Okay, let's move. So here, test the statistic. The symbol of chi-square is x squared, but we read it as chi-square, not x square. Chi-square equals summation O minus E, and round the square root value divided by E, where O is the observed frequency and E is the expected frequency. Again, O is observed and E is the expected frequency. For example, when we and later we will check the example for throwing dice, for rolling dice. Okay, the distribution of chi-square has different curves depending on the degree of freedom. See, we made it again. It is skewed to the right for smaller degrees of freedom and get more symmetric when the degree of freedom is increasing. Since the test statistic involves squaring the differences, the test statistics are all positive. Why? Check here. Observed minus the expected value. It could be positive, it could be negative. And after taking the square value, all values becomes positive. It means this. We did similar when we learned how to calculate standard deviation, right? Okay. And the p-value. The p-value is very complicated to calculate. Thus, this part I will not ask you to calculate by step by step. We can run in the free online applications. Then you can get a p-value in a few minutes. And conclusion. This is where you rather reject non-hypothesis or fail to reject non-hypothesis. The rule is if the p-value smaller than alpha, if we set alpha generally that is 0.05, then reject non-hypothesis. If the p-value greater or equal to alpha, then fail to reject. Okay, interpretation. This is where you interpret in real-world terms and conclude to the test. The conclusion for the hypothesis test is that you either have enough evidence. Again, you either have enough evidence to show the alternative hypothesis is true, or you don't have enough evidence to show that is true. That is true. Okay. Do you have enough evidence? It depends on your calculation, especially the p-value. Okay, example 11.1.1. Hypothesis test with chi-square using formula. Okay, is there a relationship between an autism and breastfeeding? To determine if there is, a researcher asked the mothers of autistic and non-autistic children to say what time period they breastfed their children. The data is in the table 11.1.1. Okay. Do the data provide enough evidence to show that breastfeeding and autism are independent? Test at the 1% level. This time the level alpha is 0.01, not 0.05. Why? Depends on your purpose. Here, let's check here. Okay, and in the first column, autism, yes and no. And about the breastfeeding timeline, no breastfeeding, less than 2 months, 2 through 6 months, more than 6 months. And now we can check here. Yes, autism, no autism. Yes, autism, 241 plus 198 plus 164 plus 215. The total is 818. And now the sum of the column, none, it means no breastfeeding of the baby. 241 plus 20, the sum is 261. Less than 2 months, 198 plus 25, that is 223. The same way. So the total babies are 934. And here, state the non-hypothesis and alternative hypothesis and the label. The label alpha is 0.01 as given by the question. And the non-hypothesis, breastfeeding and autism are independent. I cannot say breastfeeding causes autism. I cannot say that. I cannot say because they just a relationship. We can find a relationship, but it doesn't mean breastfeeding or not breastfeeding will cause autism. Is it okay? And the alternative hypothesis is breastfeeding and autism are dependent. It means they have a relationship, but again, it doesn't mean if the mommy doesn't have any breastfeeding and the baby will be autism. It doesn't mean that. Okay, test. Okay, something wrong with the computer. Okay, then sorry. Okay, test. Because I forgot to move the computer. Okay. Okay. Test. 1, 2, 1, 2, 1, 2. Test. Okay. Okay. Test. Okay. And set and check assumption for the hypothesis test. A random sample of breastfeeding time frame and autism independence were taken, and expected frequency for each cell are greater than or equal to 5. Expected value, okay, greater than or equal to 5. That's okay, because here each cell is the minimum is 20, so it fulfill this condition. 3. All expected frequency are more than 5. Yet you fulfill this question. Okay. Find the test statistic and p-value, and here test statistic. Find first. Find the test. Okay. Find the expected frequencies for each cell. Here E. Autism and no breastfeeding. That is 18 times 261 divided by the sum. The total 934. Again, expected value. Autism and no breastfeeding here. Autism, yes, here. And no breastfeeding here. 241. Times the total add 818. This one times this one and divided by this one. And the value is 228. And the next one, expected value, autism and the breastfeeding is less than 2 months. Here, add 818 times 223 divided by the total number 934. It looks like here. 198 times 818 divided by 934. And the third one, autism, 164 times 818 divided by 934. And the number 4, 215 times 818 divided by 934. And here, all the values are here. All values are here. And other are done similar. It is easier to do the calculation for the test statistic with a table, and the other table we can check here. You can check the observed 241, 198, 164, and 215, and the expected value of the calculation here. Expected value is the total number times the individual number divided by the total autism times the individual autism divided by total babies. That's 228. The same way, like this one, expected value. Here. And now calculate the observation minus expected value, 241 minus this one, and we get 12 and some decimals. We get 2 and decimals, and minus 3 and decimals, minus 12 and decimals, and minus 2 and decimals. Okay, here. And the square value of observed minus expected value, like this one. Then divided by expected value, this 154 divided by here, and the value is 0.674, like this one. And get the value here. get value here. And later, summation of those values together, that's this one. Like this formula. Chi-square equals summation to add them all up. The square value divided by the E value, and the statistical value is like this one, which is total, the lesser column in here, and degree of freedom, 2 minus 1 and 4 minus 1. How can determine the degree of freedom? Degree of freedom, check here. Autism, yes or no? Thus, two options. How can I say two items? And breastfeeding timeline, 4 items. First item, none, no breastfeeding. Second one, less than 2 months. Third one, 2 through 6 months. The number 4, more than 6 months. Thus, the degree of freedom here, 4 minus 1. Here, 2 minus 1, 4 minus 1. Degree of freedom, 2 minus 1 times 4 minus 1. That is 3. Then run the t-test and got the chi-square value. The value is 0.010, like this one. Thus, fail to reject non-hypothesis since the p-value is more than 0.01. Interpretation. There is not enough evidence to show the breastfeeding and autism are dependent. This means you cannot say that whether a child is breastfed or not will not indicate if that child will be diagnosed as an autism boy or girl. But personally, you may observe something here. In the past, we always said the alpha at the level 0.05. If we think the p-value, the alpha level is 0.01, what do we think about that? Yes, the p-value is a little bit greater than 0.01. I think it's significant. But here, the question said the alpha level at 0.01. Otherwise, if we get used to set the alpha level at 0.05, this situation, yes, we can say that there is enough evidence to show breastfeeding and autism are dependent. And maybe breastfeeding causes the reason A, and reason A causes reason B. Reason B causes the autism. Maybe. We cannot say the breastfeeding causes the autism. We cannot say that. We can say more breastfeeding, the lower the autism. But what's the mechanism? We don't know that. And to run this, sure, later I will show the evidence. I will show the website. Then we can run this. You can run this. Okay. To run this. Okay. Sorry, I may postpone the break time for a while. Okay. And now we can have this. Okay, if we have chance to use the chi-square calculator, chi-square calculator like this one. Oh, let me show you how to do this. Add groups. let me copy the information here. Oh, sorry. Okay, 241, 198. 241, 198. And 164 to 15. 164 to 15. Okay, sorry, I forgot to give. Okay, I just copied and pasted the website, and you can follow my steps here. And then 20, 25, 27, 44. 20, 25, 27, 44. Okay, please use your cell phone to run the number like this, like 30 seconds. Okay, let me drink in my oolong tea. Is that okay for you? Okay, and after that, we can click. Oh, let me have this. Then I can click calculate. Calculate. See? Let's check it. Let's check it. Group 1, category 241, 20. The total for the non-breastfeeding is 261. Like this one, like this one. And expected frequencies, 228 plus, 228, about this. Do you remember how to calculate this? Expected frequency here. Let's review it again. Expected frequency, cell A and B, then we can write it as expected value, parentheses A and B, n times raw total divided by n, times column total divided by n. That is raw total minus column total divided by n. Raw total minus column total divided by n. Like this one. Let's review here. Here, 241 times 818 divided by 934, divided by 34. And here is expected value of this, 228 and some decimals. And here 190 98 times 818 divided by 934. That is expected value here. Expected value 818 times 261 divided by 934. The expected value is here. Get it? Let's move here. Thus, we know that expected value is here. And sure, during the exam next week, I may have some examples for you. You can test it. And the chi-square point, the observed value 241 minus 228, and get square value. The results look like this. And the chi-square value 11.2, and the p-value is 0.0106, not significant when p-value is smaller than 0.01. Sure, if we set the label at 0.05, calculate again. And if we change the alpha level to the p-value is 0.0106 and significant at p-value smaller than 0.05. But generally speaking, we use 0.05. But this time, the chi-square, the question used 0.01 advertise. Okay, is it okay? Oh, how about have a 10-minute break and later we can come back and check the attendance? Okay, 10-minute break. See you later.